Good Monday morning, everybody. I hope you guys had a great weekend and you were able to get outside and enjoy that amazing spring weather, doing some yard work, going for a walk, riding your bike, whatever you're able to do to get some fresh air and put some sanity back into your lives with all this social isolation. You may notice, I don't know if the lighting's good enough in here to show you my new tan I'm sporting after 2 days of working in the yard. I'm hoping all the red is going to turn to brown in the next couple days. I didn't put any sunscreen on, but I did wear a hat. Anyway, hope you're well. Today's going to be one of your favorite lessons because it's short and sweet, and I think it's pretty interesting too. There's lots of practical applications. So today we're doing a corrosion, the rusting of metals, and then tomorrow and Wednesday is electrolytic cells. And then Thursday is cell stoichiometry using Faraday's constant, and then we're done. We'll wrap up the chapter and the unit on Friday, and then we're moving on to our last unit. We are going to finish this course early, due in large part to you guys, working hard, staying on task, and moving through the material at a good pace. All right, so speaking of, let's move through this material. So corrosion. Pretty interesting. Corrosion. So we're working in your study guide on page 226, 227. If you would like to follow along in the notes and fill that in. So the first thing you have to do, we're skipping the Haber process and corrosion of iron. We'll do that later on in the notes. All right, define corrosion. So it's an electrochemical process or a redox reaction. And it involves a metal. And the metal is always the reducing agent, and it will react with substances in the environment, which would be our oxidizing agents, and it will return metal to an ore-like state. When we mine metals in the earth, we rarely find them in their pure metal form. They're usually oxides. So for example, aluminum metal, you don't find it as aluminum, you find it as aluminum oxide, Al2O3, or bauxite is the name of the mineral, the ore. So most metals are mined as their ores in their oxidized form. Okay. We live in an oxygen-rich environment. 18% of our atmosphere is oxygen, and oxygen is a pretty good oxidizing agent. So metals are constantly being attacked as reducing agents. They are constantly being attacked by the oxidizing agents. And as a result, we have oxidation or corrosion of metals occurring spontaneously. It just happens on its own because oxygen as an oxidizing agent is above most metals as a reducing agent on our table of relative strengths. Now, we need to produce new metals constantly because we're losing metals constantly to the consistent, ever-present corrosion that's going on. So let's take a look at this example. So we have two vehicles that have been sitting outside for about 60 years. So we've got this aluminum pop-up ice fishing trailer, which is really cool. So this lid lifts up, and you've got two little seats in there, a little tent folds down, and little windows you can open up to put your fishing rod out there and go ice fishing. Amazing. Actually, you wouldn't do that. Those windows would be for looking out, and ice fishing, you'd be dropping your line straight through a hole under the floor. So anyway, this thing's 60 years old. It's in great shape. Now, this Humber Super Snipe, also same age, is in terrible shape. So the question is, why does the aluminum not appear to be rusting, but the iron in this Humber Super Snipe is severely corroded? Corrosion of iron versus corrosion of aluminum. So what's going on? Okay, big idea number one. Whoops. So aluminum versus iron, the great rust off. So when iron corrodes, combines with oxygen as the oxidizing agent and iron as or aluminum as the reducing agent, we get Al2O3 or aluminum oxide. So the aluminum does corrode, and it does do this spontaneously. If you look on the table of relative strengths, right there, we have aluminum is actually a very strong reducing agent. It is way down here. 1, 2, 3, 4, 5, 6, 7. So it will oxidize with almost anything, even just water without oxygen, it will corrode. So why does it look so great after 60 years of corroding? So here's the story. When aluminum oxide forms, it adheres tightly to the aluminum atoms below, forming an airtight barrier, effectively sealing off the aluminum underneath. So the way I describe it to students is it's kind of like it paints itself as it's rusting. Paints itself with an oxide coating. And what that does is prevents any further corrosion because it's now sealed itself off so that no more oxygen can get in. So if you have anything that's aluminum, it probably has this dull gray color to it. You also see that on these pots. So these have already been corroded or oxidized, and that's what oxidized aluminum looks like. When it hasn't been, it looks like this super shiny piston. Yes, piston. It's supposed to go in that cylinder. So fresh, new oxygen or aluminum is super shiny, and then it immediately oxidizes and gets the dull gray color. Okay. Iron is a different story. Iron oxides, when they form, do not adhere to their metal. Instead, they flake off, exposing the next layer of iron to the air, so you get continual oxidation, continual rusting as the layers slough off. It's kind of like a scab that just keeps falling off and exposing the wound underneath. More damage, and eventually you get holes. If we go back and look at the Humber Super Snipe, you can see in this section how layer after layer has been corroded and there's nothing left. All of the iron is gone in that section of the car. Okay, so the redox reaction, you need to know this one, but it's in your table of relative strengths, so you don't have to figure it out. You just have to be able to find it. So here's iron. So you can see that it's also a strong reducing agent, but it's not as strong as aluminum. But it will still spontaneously react with oxygen when it's in water. So here's our oxidizing agent, and there's always moisture, some moisture in the air. Even worse is when it's raining or something sitting on the ground where there's a much higher moisture content, then you have even more corrosion. And as a side note, if you really want things to rust quickly with oxygen, add an acid. So when you have an aqueous acid, you get an even stronger oxidizing agent. And you can see on the table of relative strengths that these guys are pretty high up here. So here's our strongest oxidizing agent. So they're reasonably strong. And of course, more importantly, they are spontaneous. Our oxidizing agent sits above the reducing agent. So the reactions are, let's jump back for a second. We have Fe solid going to Fe2 plus as our reducing agent. Oxygen combining with water, 4 electrons gained, and it makes hydroxide. So here are the reactions. That oxygen, when we cut it in half, just so that we could balance the electrons easily with 2 gained and 2 lost. So the balanced redox reaction here would be iron solid reacts with water and oxygen to make hydroxide, basic, and Fe2 plus, aqueous. And Fe2 plus, I'm just looking on my sheet. Actually, I'll grab my data book. Fe2 plus has a color. So you're going to see a color change on this one if you were doing it in the lab, in a beaker, in a petri dish. Fe2 is lime green. So you're going to produce a green color with the Fe2 plus. Interesting. Now that property changes when it combines with the hydroxide. So what happens is the reaction will dry out and then you'll get FeOH2 solid or rust. Cell potential for that. So if you were going to calculate the cell potential, our cathode is our strongest oxidizing agent gaining electrons. So here's the cathode. Here's the cell potential of the cathode, 0.40 volts, minus the anode, which is the metal rusting, and it's negative 0.45 volts. 0.4 minus a negative becomes a positive positive 0.85 volts. So while your car is rusting, it's also generating a small amount of voltage, which you could maybe use to play the radio or power the headlights if you were really rusting at a rapid rate and had a circuit hooked up to the iron frame of your car. Wouldn't that be convenient? Okay, so iron needs water and oxygen from the air to rust spontaneously, and we can see it's spontaneous because it's positive. Positive cell potential means a spontaneous voltaic cell. A little extra information, Fe2 plus can lose another electron and form Fe3 plus, which then makes FeOH3. This is the more common form of rust that you'll see, that yellow brownish solid. And then it can also grab onto 3 water molecules and turn to a red-brown solid. And we see all those colors in this rusting anchor off of this ship. Red, brown, and yellow, brown. So rusting can be pretty complex, but for Chem 30, this is really what you need to know and recognize that it's spontaneous at 0.85 volts. And again, you can figure that out. You don't need to memorize it. You just need to remember this combo on your table of relative strengths right there. That's the key to rusting in an oxygen-rich environment. Okay, now some interesting stuff. Okay, picture's worth 1,000 words. So here's rusting. We've got a solid iron bar, and it's in a wet environment exposed to the air. And this becomes our strongest oxidizing agent, or our cathode, and this becomes the anode. So the interesting thing about this metal bar in a wet oxygen environment is it becomes a small battery, a small voltaic cell. The Fe loses 2 electrons, sends them this way. Put that to black, loses 2 electrons. So there's the electrons traveling through the metal, and they combine with the water and the oxygen to make hydroxide. So the hydroxide combines with the Fe2 plus to make FeOH2, which is this solid that's building up, or rust. And at the same time, we've got this completed circuit. And so we are generating positive 0.85 volts. Now to make this thing work really well, let's add some salt. So now we have our aqueous electrical conductor, or like our salt bridge. And now this thing will rust really fast and spontaneously and efficiently with our 2 half reactions at the anode and the cathode. If we put signs, we'd call that the positive end of the voltaic cell, and that would be the negative end. Okay, that's in your textbook as well, that picture. Rolling along. Okay, so some interesting things for you. Things that affect the rate of corrosion. Metals corrode faster when in contact with another metal, because this gives you 2 separate electrodes for a more efficient voltaic cell. So a cool example of this is the Statue of Liberty. So the Statue of Liberty is made of copper skin, but she had iron ribs. And they didn't realize in the 1800s when they built her that iron is more easily oxidized than copper. So we have our 2 electrodes. Iron becomes the anode, copper becomes the cathode. And if you have any sort of acid rain to make it efficient, then you have oxygen and water in your half cell with the copper. And you saw the reaction that we just saw. So as a result, the Statue of Liberty lost her iron ribs. They were severely corroded. To fix the problem, they used iron bolts. Not too smart. That exaggerated the problem and made it even worse. So then finally, I think it was the 1990s or I think 1990s, when they changed out all the iron ribs for stainless steel. Cost a little bit of money, but stainless steel will not corrode. It is an extremely weak reducing agent, so we have a non-spontaneous redox reaction. In other words, nothing happens. So she's in good shape now thanks to her stainless steel alloy ribs. As I said, salt water speeds up corrosion because you're basically making a salt bridge. And so if you really want to speed up corrosion, put salt on the roads. So it's good for melting the ice, but it's tough on cars. So you can see this example of this car is completely rusted out around the wheel well, because when the wheel is turning, it's spraying salt up into the metal wheel well, and that's where all the corrosion is occurring, and that's why you always see rusting first around the wheel wells, where the salty water from the roads is sprayed onto the metal frame, creating a nice effective salt bridge to really speed up the corrosion of that solid iron in a wet, oxygen-rich environment. Okay, moving on. Hey, I think we're like half done our lesson. Love it. Okay, so you need to know ways to prevent or protect against corrosion. And there's 4 that we're going to look at, and some of them are kind of common sense. So number 1 is prevent oxygen and water from contacting the metal. So how can you do that? You can do it with paint. This is why we paint objects, especially metals. Coat them in grease, bicycle chains, or coat them in a layer of plastic. Something that will cover the metal. Cutlery has a stainless steel coating, but they're iron in the center. I once bought a set of cutlery from Costco, brought it home, put it in the dishwasher, warm, moist environment. It came out and it was all rusty. And I was like, what? How is this possible? This is a brand new set of cutlery. Like, how can it be rusting? So then I got my magnifying glass out and I took a look at it up close, and I could see there was tiny little holes in the stainless steel coating. They hadn't put a thick enough layer on, and anywhere there was little tiny micro pockets or holes in it, it had immediately corroded in the dishwasher. Oh yeah, and of course the dishwasher has an electrolyte in it too with the soap. So first wash, it was already rusted. So that was an interesting lesson for me about electroplating objects and putting a thick enough layer on to do the job. So I took them back and got another set, because we all know Costco is great for returns. Here's an example of an iron pillar in India that has almost no corrosion, and that's because the air is very dry and unpolluted in that particular part of India. That iron post has been sitting there for 1,500 years without much corrosion. So oxygen doesn't do very well on its own. It really needs the water to make it an effective oxidizing agent. Okay, option number 2, and we talked about this, make a metal alloy. So when you mix metals into alloys, it changes their properties and can really reduce the loss of electrons. It turns them into really weak reducing agents. So stainless steel is an example of that. So you might be interested to know, where does stainless steel come from? So where does steel come from? So we have 3 things here. You can start with iron, which is a good reducing agent, terrible for corrosion. If you add a little bit of carbon to the iron, you get steel. So steel doesn't rust as easily as iron does. If you take steel, or iron and carbon, and you add chromium, then you get stainless steel, which is a very weak reducing agent and does not corrode. So it's an alloy of a nonmetal and 2 metals to get stainless steel. So that's option number 2. So just to review, paint it, coat it in grease or plastic to prevent the oxygen and water from contacting the metal. Add something to the metal to make it an alloy that is less likely to corrode. Now we're getting into my favorite and the interesting ones. So cathodic protection, what the heck is that? Okay, so in cathodic protection, you use a really strong reducing agent. Zinc or magnesium are the best 2. I'm going to show you why. Okay, here's iron, and here's zinc, which is even stronger than iron. Or even better, here's magnesium. So zinc and magnesium are really strong reducing agents. And what that means is, for cathodic protection, you literally bolt or strap the zinc or magnesium onto the surface of the iron. Why would you do that? Because these are stronger. They will oxidize more readily and lose their electrons first, protecting the iron. So what you're really doing is putting a stronger reducing agent on the iron so it loses its electrons first, which protects the iron and prevents it from losing its electrons. So what does it look like? Well, here's an iron pipe, which, by the way, is coated in plastic. So this is Fe. So they've coated it in plastic to try and keep the water away. But when you bury these pipes, they get nicks in the plastic. Stuff happens, so water and oxygen can get in spots. So then they've taken this block of, I think this one's zinc. I'm sure it is zinc. And they've just got a wire, whoops, here it is, coming from the block of zinc, and they've attached it to the pipe. So this will lose its electrons to the oxygen and water before the iron will. So that's your strongest reducing agent, and they've got 2 of them. If you drive around Red Deer, you'll see signs that say warning, buried cathodic protection. They're usually in the alleyways, and they'll have a sign and then they'll have a lid literally right on the road. So they lift up, those lids are locked, by the way, but they'll open them up and they'll just take a look and see the condition of the zinc. Because this stuff gets used up over time. It's losing its electrons and becoming zinc 2+. So they have to replace the anodes. And I don't know if they do it annually or every couple years. Depends on the environment, I guess, where you are in the country. But those anodes do need to get replaced to protect the iron. So once they're used up, new ones are needed. They also use them on ships, marine vessels, underground pipes, underground tanks, underground anything that's got iron will have buried cathodic protection to help it out. By the way, this has a great name, this anode. It is called, I don't see it here, a sacrificial anode. How awesome is that? So they are sacrificing the zinc to save the iron. Okay, option number 4 is galvanization. And in galvanization, it's kind of like a sacrificial anode, but instead of using a chunk of zinc, they are coating the metal with zinc. So they'll take an iron bucket or an iron nail and they will dip it into hot molten zinc to coat it and then pull it out. The zinc cools, hardens, and then you have a zinc coated nail or bucket. And again, the zinc will lose its electrons before the iron does, preventing corrosion of the iron. You'll see this on all the lamp posts. Oh, my printing is messy today. You'll see it on all the lamp posts around Red Deer. They'll have this kind of weird blotchy gray color to them. That is the galvanized paint. I helped a friend of mine. We put a bridge, an old military bridge called a Bailey Bridge from the 50s onto our ski trails out at Riverbend. We had to get a big truck to bring this bridge in. It weighed like 20 tons, but it was coated in zinc. It's really, really thick galvanization, and it had no corrosion. That thing had been sitting out in a farmer's field for 40 years, probably 50 years, maybe 70 years since the war was over. And it was in great shape because it had such a thick layer of zinc to be the sacrificial anode and protect the iron. Okay. Oh, yes, there's our term. So this is a summary of both of those methods, galvanization and cathodic protection. I'm just going to finish off the video showing you some interesting examples of this. So if you have ever been on a ski boat, a water boat with an outboard, well, even the outboard engines and inboard engines, so you've got your propeller back here. They have this little shark's fin sticking out. You might have noticed it on your boat if you have one. That is the sacrificial anode. That is where the electrons are lost to protect any iron that's in any of this head of the motor. And so here's what it looks like from underneath. They're pointing to it, and this one is just about used up. Here's a bolt-on sacrificial anode. So you just bolt it onto your boat. Here's what it's looked like when it's used up. Not completely used up, but enough that I would replace it. Here's what a motor looks like when it doesn't have the sacrificial anode. It's missing or used up. You can see this thing is just being oxidized like crazy. It's in terrible shape. So you really have to look after those anodes and maintain them. Otherwise, your iron corrodes. Okay, last couple examples, and then we're done. So gas stations, any gas station that has an underground steel tank is going to have buried cathodic protection. In this case, they're using magnesium to protect, and so it is the strongest reducing agent, or the sacrificial anode. Okay, man, that's messy. Ugh. The last example is offshore oil platforms. Any structure that's being built out in the ocean where you have salt water and an extreme rate of corrosion, you can use a power supply to force your electrons. So you've got an anode, but instead of the anode just casually, spontaneously supplying the electrons, you've got a power supply that pulls them in and pushes them out and forces them onto the structure that you want to protect. And the interesting thing about this one is it can steal electrons from chloride. 4Cl minus can go to 2 chlorine and give up 4 electrons. So that's kind of cool that this anode can steal from salt water, but at the same time, oxygen and water can steal those 4 electrons back as the strongest oxidizing agent. So you have this battle going on. So you usually have to replace those anodes as well. Always protecting the metals so they don't return to their ore-like state. Hey, we're done. How sweet was that? Nice way to start the week. I would suggest you at least read over these questions, and you can write down the answers in your textbook, from your textbook, or read them over and go, do I know that? Do I know that? Do I understand this? Corrosion is a really nice, simple, light topic. You don't really need to do a lot of practice to understand it and make sense of it. Just got to remember those key redox reactions involved and the idea of the strength of the oxidizing agent, oxygen and water, relative to the reducing agent, iron, the ways to protect iron, and all of the notes we went through. Anyway, I'm rambling. I'm going to stop. Okay. Hope you guys have a nice afternoon. And tomorrow and Wednesday, we'll get into electrolytic cells. This is going to look just like day 1 and day 2 where we did the voltaic cells, except now these guys are non-spontaneous, which is a little different to get your head around, but I think you'll find them pretty straightforward. Okay. Have a great afternoon.